Welcome to the DPP discussion of queuing. So in the last two lectures we have discussed queuing theory elaborately in class. So I have framed some questions. So let us look at them. A repair shop attended by a single mechanic has an average of 4 customers per hour. So lambda is 4 per hour. You bring small appliances for repair. The mechanic inspects them for defects and quite often can fix them right away or otherwise render a diagnosis. This takes him 6 minutes on an average. So in 1 hour there are 60 minutes. So service time is 6 minutes. So service rate will be 10 per hour because 60 divided by 6 is equals to 10. Arrivals as Poisson and service rate has exponential. So this is Markovian, Markov chain, Markovian distribution. You are required to find the probability of finding at least one customer in the shop. Probability of at least one customer. So what is the probability? The number of customers are greater than or equal to 1. Okay, so it will be P1 plus P2. Can I say it is 1 minus P0? So the rho is nothing but lambda by mu. It is nothing but 4 by 10. And P naught is 1 minus rho. If no data is given, we will assume that it's a single server, single queue system. So it is nothing but rho. So answer will be 0.4. A maintenance service facility has Poisson arrival rates, negative exponential service time, and operates on a first come first serve basis. Breakdown occurs at an average of 3 per day. So here the time unit basis is 1 day with range of 0 to 8. Okay, so the maximum people that can accommodate is 8. The maintenance per day with a range of 0 to 7. The mean waiting time of an item to be served would be. Mean refers to the queue. So one data missing here. The maintenance per day is 6 with a range of 0 to 7 because excluding the person who is being served, it's a queue. All right. So now the mean waiting time of an item to be served would be mu is 6 per day. So what is rho? Rho is lambda by mu is nothing but 1 by 2. So as I told you, mean waiting time means it is referred to Q. It is referred to Q. So LQ is nothing but rho square divided by 1 minus rho is 1 by 2 square divided by 1 minus 1 by 2. So comes out to be 1 by 2. So waiting time in Q is nothing but LQ divided by lambda. Okay, so LQ is 1 by 2 and lambda is 3. So 1 by 6 day. Arrival at a telephone booth are considered to be poison where there is average time of 10 minutes between the successive arrivals. So it can I say 6 per hour. The length of whole call is distributed exponentially with a mean of 3 minutes. So mu is 60 by 3 means 20 per hour. The probability that arrival does not have to wait before service is. When the arrival doesn't have to wait, if there is nobody in the system, arrival will come directly enter into the service. So we have to find out P naught, which is nothing but 1 minus rho, and rho is nothing but 6 by 20. So 1 minus 6 by 20 means 14 by 20 comes out to be 0.7. In a single server infinite population queuing model, arrival follow a Poisson distribution with lambda is not 4 per hour. The service time are exponential with a mean service equal to 12 minutes. So convert into same unit of hour. So mu will be 60 by 12 per hour. So 5 per hour. Okay. So these things should be in the same unit. The expected length of queue L cube is nothing but rho square divided by 1 minus rho. So rho is 4 by 5. 4 by 5 square divided by 1 minus 4 by 5. So 16 divided by 25 divided by 1 by 5. So 16 by 5. So 3.2. For a single server with Poisson arrival and exponential service time, the arrival rate is 12 per hour. Which one of the following service rates will provide a steady state infinite queue length? Steady state infinite queue length. See if C is equals to 12 and 24. I mean, if the rho is greater than 1, the queue will explode. If rho is greater than Q will explode, it will never converge. Never converge. Never converge means no steady state. No steady state. So let us say if the mu is 6, here how much is the rho 2? Explode. It's 1.2. Explode. 1. Explode. And this is 0.5. So only this service rate will converge, all the other three queues will be exploding. In a single channel queuing model, the customer arrive at a rate of 12 and the service rate is 24 per hour. The expected time the customer is in the queue is Q. So WQ is nothing but LQ by lambda. So here rho is 1 by 2. So LQ is rho square divided by 1 minus rho means 1 by 2 square divided by 1 minus 1 by 2. So it is 1 by 2. So LQ is nothing but we have to find out sorry, LQ is nothing but 1 by 2. So we have to find out WQ. We have to find out WQ. 1 by 2 divided by lambda is 12, and we have to find out in minutes multiplied by 65. So 2.5 minutes. Customers arrive at a ticket counter at a rate of 50 per hour. and tickets are issued in the order of their arrival. The average time taken for issuing a ticket is 1 minute. So mu is 60 per hour. 60 tickets are issued. These units should be same. Assuming that customer arrive from a Poisson process and service times are exponentially distributed, the average waiting time in queue. So here LQ is nothing but rho is 5 by 6. So 5 by 6 square divided by 1 minus 5 by 6. 25 divided by 6. Correct? Now WQ is nothing but 25 by 6 divided by 50. And I have to convert into our minutes. Multiplied by 60. 0, 0, 6. 6 cancel out. So 5 minutes. So here there is a thing that you have to mug up. What the question says that suppose a customer is approaching. A customer is approaching. What is the guarantee that customer will be served in the time interval delta t? Within the delta t time, customer will avail the service and go away. So that probability is nothing but service rate multiplied by that time interval. You have to mug up this formula as some of the certain things I told you to mug up. And if you go MTech Industrial Engineering, you will be proving. Like there was one table now, I asked you to mug up. So this is another thing. Probability that customer will come and within delta t time he will leave the service after availing it is service rate into delta t. Now suppose there are m servers. Their number of servers are m. So service rate will multiply by that, na? If there are m servers, number of servers will be multiplied by mu into delta t. It's a directly formula. So please remember this one. Of course, it may appear in some exam. That's the reason I have given. Which one of the following distribution is followed by number of arrivals? Poisson arrival, because it's a Markovian. Markovian distribution means Poisson arrival, whatever we have discussed. So answer is B. The Kendall notation representing the Q model, the first position represents the probability of arrival. Second position is the probability of service. Third one is number of server. Fourth one is a Q discipline. Then whether Q is finite or infinite, and finally the calling source population. So these were some of the questions I have framed for DPP. I hope you enjoy it. All the best.